Okay.
So hello everybody, this is the second lecture for the course about application of topology in online social network and blockchain network. Professor Cuneyt unit, Akçora is going to start. Let's see what he's going to explain to us. Please.
Thank you very much, Rocio. So in the first day, if you remember, we just covered the TDA basics and we defined simplexes, simplicial complexes, and so on. If you missed the first day, don't worry, because now I'm going to talk about these things in the graph setting. So I will teach similar things. You don't need to know the first day. However, if you know the first day, the advantage is that now you can go and read TDA articles and you will not get lost in the terminology. Because the terminology is coming from mathematicians, it can be tedious for computer scientists a little bit, or statisticians, let's say. So here is a summary of what the persistent homology, which is a subfield in TDA, is doing mainly. We are given X data points in D-dimensional space. In this D-dimensional space, we find pairwise distances between data points. And then we use a filtration threshold on distances from 0 to maximum. This 0 is written here as a minimum, but the minimum could be anything in reality. It can be any scalar value, for example, -10 or 15 or something like this. And then by using this filtration threshold that we use as alpha, also in the literature, people use epsilon for this, so they are the same thing. We create simplices based on pairwise distances. What this means is that if we have two data points, we compute their similarity, and let's say the similarity is a value alpha 1. If this similarity is less than the alpha threshold that we are using, then we create this edge between two data points. This is how we use the distance. And then when we connect data points like this, a simplicial complex appears. A simplicial complex is very similar to a graph. However, unlike a graph, in a simplicial complex, we have higher dimensional vertices. So for example, in a simplicial complex, you may have a triangle that is a vertex itself. So this is called a face. For example, this is a two simplex. So that means it's like you have diamonds and other shapes in your graph. So not only we have nodes or edges, now we have simplices in the graph. So this is the only thing that is really happening in a simplicial complex. After that, we look at the simplicial complex and we identify which holes persist. By holes, we mean some part of the missing data. Consider this as a hole in your cheese. So there is a hole and we are trying to determine its dimensions. And the useful information is that why this hole exists in your cheese, for example, and can we do something with that information. Afterward, we saw persistence diagrams, persistence landscape, barcodes, persistence silhouette. These are different ways to vectorize the persistent homology output. Remember, in the persistent homology output, it was giving us a list of, for example, zero-dimensional holes and their birth dates and death dates. So for every hole, we have a pair of BD, and we may have multiple zero-dimensional holes, or we may have one-dimensional holes similarly given with birth and death dates. However, this output, which is recorded in a persistence diagram, is not so useful. So we need to vectorize it. And by vectorize, I mean that we need to somehow serialize it in a nice vector so that this vector can be used in machine learning tasks. So this is called the vectorization. Yeah, these are the main points in applying persistent homology to point clouds. Now, how do we do topological data analysis on graphs? In this section, my aim is to explain how we can construct a simplicial complex on a graph. Here is the summary of pH again, but this time I have made changes to apply persistent homology to graphs. So instead of X data points, we are given X graphs. And in graphs, we don't talk about D dimensions, for example, because graphs have no dimensions, let's say. Then we find edge or node features instead of pairwise distances. And we use these edge or node features as activation values. In 2 slides, I will come to what I mean by edge or node activations. So far in persistent homology in data point clouds, we are used to edge activations. Like an edge appears if the distance between 2 data points is less than the alpha threshold. So far, we have always seen edge features. But there is also the node features that I will show. These are called edge or node activations. Then we are going to use a filtration threshold on not distances, but edge or node activations, and again from minimum to maximum. We are going to create simplices and the simplicial complex out of them, and we will identify certain topological features. What are they? These are dimensional holes that are missing. So the idea of topological features remains the same, from point clouds to graphs. Then we are going to identify which holes persist, and then we will vectorize the output, and we will use the vectorization in graph machine learning tasks. What are these? There are mainly 3 or 4 tasks. One of them is node classification. For example, in blockchains, when you are looking at Bitcoin addresses, if you want to identify which address belongs to ransomware hackers, this is node classification. You classify nodes as belonging to ransomware hackers or to ordinary people. Then we have edge classification, which is classifying edges to say this is, for example, a ransomware payment between 2 addresses. We have graph classification that is commonly used in molecular biological networks. For example, you have multiple molecules, drugs, and so on. And for example, it can be an enzyme, and then you have the labels coming from domain experts that says this enzyme, for example, has this label. A 4th task is actually subgraph classification, which is a part of graph classification. We don't cover it explicitly, but subgraph classification can be thought of as the 4th type of classification task. So these are the main points in applying persistent homology to graphs. So here is my simplified classification about persistent homology. We basically have 2 types of pH on graphs. By pH, I mean persistent homology. The first type is edge activation based. That is very similar to what we covered in the data point setting. We have Viatori strips, we have Che. So we create a simplicial complex based on node distances. This node distance is defined in terms of the edge weight or distance that connects the 2 nodes. So in this approach, edges appear along the filtration threshold between 2 nodes. So in the very beginning, we have each node as isolated, and then based on distance, some of the edges are activated as you change the filtration threshold, and you create a simplicial complex by using this. This is the first approach, edge activation based. In the second approach, we have node activation based. This is usually called sub or super level filtration. We create a simplicial complex based on node activation. So in the first case, edges were appearing. Now nodes are going to appear. Nodes are activated based on their activation values, which can come from domain expertise. For example, it can be that some of the nodes are atoms and we have their weights. So we can do a filtration on atomic weights of elements in, for example, molecular networks and so on. In this node activation-based approach, nodes appear along the filtration threshold, and edges that exist between the activated nodes also activate. So in a sense, each time some of the nodes are going to be activated, let's say, I will change the color. Let's say this node and this node gets activated at one threshold. If there is an edge between them, it is also activated. If 3 nodes are activated, all of the edges between them are activated. So nodes appear and then edges appear between them. I will give an example on the graph and I will show you how it works in detail. So consider the graph below where we have edge weights that indicate distances. For example, here it says the distance between node A and node B is 1. Between node B and C is 25. Between D and C is 60. Now, let's use a Vietoris-Rips complex. And Vietoris-Rips complex, remember, creates an edge or activates an edge between any pair of points if the distance between nodes, the dx, xi, and xj, is less than or equal to alpha, which is the filtration threshold for all ij. So let's define a filtration scale parameter, which we will increase from a minimum to a maximum. Now, what is the minimum scale? I'm showing the original graph at the top here. What is the minimum threshold that we can use? If you look at edge weights or distances, let me say edge distances, the minimum is 1 and the maximum is 100. So it seems like if I do a filtration from 1 to 100, I'm okay. I could do from 0 to 100 as well. This is called the filtration range. If you go beyond 100, for example, if you do a filtration from 0 to 500, it will not be very useful because after 100 there will not be any new edges. So you are doing filtration where everything has already appeared. Let's do from 0 to 100. And here there are 4 panels, and I am showing you simplicial complexes in each panel. So this is simplicial complex 1, this is simplicial complex 2, and so forth until the 4th one. At each simplicial complex, I am using an alpha value. For example, in the leftmost, the alpha is 0. In the second one, alpha is 1. In the third one, alpha is 3. In the last one, alpha is 100. So as you can imagine, there is a gap between the third and the 4th simplicial complex. Now, let's look at the original graph on the top right and say, if we are here in the first panel, if we are looking at distances less than or equal to 0, do we have any edges activated? As you can see, none of the edges are activated because the minimum distance is 1. So we have nodes here, we have the 6 nodes here, and none of the edges are activated. So all the nodes are isolated like this in the first simplicial complex. In the second simplicial complex, we increase the threshold to 1, and now you will see that 3 edges are activated. This one, between A and E, and between E and D are activated. In the third simplicial complex, we will increase the threshold to 3, and if we look at it, furthermore, a 4th edge will be activated, but nothing else. And now the interesting thing here is, when we do this activation, a one-dimensional hole, which is a loop, appears in the third simplicial complex. So we are going to detect this as a one-dimensional hole, which is a graph loop. Okay, graph loop, and it appears at alpha threshold 3. If we continue forward in Vietoris-Rips, eventually the distances are cumulative. For example, the distance between A and C is 26 because it sums all the edge distances. So 26. What is the maximum? I think the maximum would be between F and C, which would be 100 plus 1 plus 60. So around 160, 70, all of these nodes will be connected, even if there are edges or not. So we will have just one simplex that covers all of them. So in a sense, the one-dimensional hole is going to die, everything is going to die, so your graph will be something like a point, mathematically. Okay. Any questions here? So this was edge activation, Vietoris-Rips. Now, there are multiple questions here. The first question is, how do we define a distance based on edge weights? In the previous slide, I said that edge weights were distances, so we did not have to define a distance. In some cases, edge weights are not distances. For example, in blockchains, edge weights show the transacted amounts. So let's say you have 2 addresses and they are transacting 500 ethers, which is a cryptocurrency. And then another pair is transacting 2 ethers. How do we define distance? If you think about it, the distance between the second one and the third one should be less than the distance between the first one and the second one. So in a sense, distance between 2 and 3 should be less than the distance between 2 and 1, because we can assume that edge weight is positive. In terms of distance, if you have a larger weight, the distance should be less. So it's not easy always to define this distance. The second question is, what happens if the graph is unweighted? I have 3 alternatives for this, but there can be many things. So on a graph, you can define distances as you want. There are multiple ways. However, from the research in the last years, I have identified 3 distance types that are useful. And the first one is the graph resistance distance. In a graph, the resistance between 2 vertices measures how difficult it is for electric current to flow between 2 vertices. So graph resistance is quite popular these days because of a new publication that showed it helps distinguish 2 non-isomorphic graphs better in graph neural networks. This is the ICLR 2023 article. You can look at it, how they use the graph resistance distance. But basically, it says that you are considering the graph as if it was an electric circuit, and you are looking at the resistance between nodes, for example. Okay. Yeah. Now, the second way to define a distance is using shortest path distance. This is quite simple. We just count the number of edges along the shortest path between 2 vertices in a graph. So, for example, if I have vertex 1 and vertex 2, and if the distance between them is 3, for example, you just count it. If there is another vertex, for example, 3 with distance 1, the distance between 1 and 3, you can consider to be 3 plus 1. Or if it is completely undirected, you just count the number of edges. For example, sorry, unweighted. In this case, you would just say it is 2, because 1 plus 1. So you have to pass 2 edges on the shortest path from vertex 1 to vertex 3. This is quite easy. The third one is called the Richie curvature. This Richie curvature is something new that is coming from, if I'm not wrong, physics. And wherever I look at it, I also used it in my experiments, it tends to give the best results. So what it does is this. Richie curvature is a generalization of the Richie curvature from Riemannian geometry. It provides a way to quantify the geometric properties of the network based on connectivity and edge weights. So what that means is that in the Richie curvature, you are given an undirected graph like the one shown here. And then if you apply the Richie curvature, it's going to extend some of the edges. And these are the edges that are between communities, distinct communities, because we consider this to be one community and this to be another community. This network is known as the Zakari's Karate Club. That's a very famous toy network in the literature. We always test our methods on this network first. Zakari's Karate Network. Yeah. So Richie curvature is extending the edges between communities and then shortening them between nodes of the same community. Then you can actually cut the edges. In this paper, they are using Richie curvature for community detection. But in our case, we basically redefine edge weights with Richie curvature. And in Richie curvature, if 2 nodes belong to the same community, not the same community, but if their neighbors are also connected, then the edge weight becomes something positive, big. If 2 nodes share neighborhoods that are not overlapping, then the edge weight between them becomes negative. And we use these Richie values as a kind of distance. Yeah. The third question is, what happens if the graph is directed? So far, we have only seen undirected graphs that can be weighted or unweighted. But what happens if the graph itself is directed? We can use the distance measures introduced in the first question, but we only focus on one type of edge. For example, we can define distances based on incoming edges or outgoing edges. In our research work, usually we ignore the edge direction and we consider the directed graph as undirected. Of course, it is a simplification, but in most cases, it works well. So we cannot cover all distances for undirected and unweighted graphs in this course. I was trying to find a good reference for the graph distances. There is a good survey paper on graph edit distance that finds the distance between two graphs. But I have not found a good reference to find node distances on a graph. So if you have a good reference, please let me know. So 3 questions, and we are done with edge activations. So to summarize, in edge activation, you somehow need to define edge distances or edge weights, and then based on these edge weights, you will do a filtration. And the filtration is exactly similar to what we used to do in the point cloud setting. Okay. Now, what about persistent homology with node activations? Consider the graph below where we have features on nodes. This time, these, for example, 60 belongs to this node D. It can be the age, for example. It can be the age of a person. There are no edge features here, as you can see. In the previous graph, we had features on edges. In node activation, there are 2 types of filtrations. In the sublevel filtration, you define a minimum and a maximum scale, and then you filter from minimum to maximum. In the super level, we do filtration from maximum to minimum. The resulting simplicial complexes are not the same. So in some articles, I have seen people do sublevel filtration, create a persistent homology vector, and then concatenate it with the same vector coming from the super level. So they use, for example, one vector from sublevel and one vector from super level in classification tasks. Concatenate them directly. Now, let's do, this should be node. Let's do a node activation on this graph. We will start from minimum scale 10. Why? Because we have the minimum scale 10 here. And the maximum is 80 because we have 80 here. Let's do this. In this filtration, nodes do not appear isolated in the very beginning. Only the nodes that are activated are shown in the simplicial complex. For example, if we use 10, only node E is active. So it appears itself. Then, if we increase the filtration threshold to 30, which nodes appear? Well, A appears. That's it. And the edge existed between A and B, so this edge is also activated. Then, if we increase the threshold to 60, D appears, B appears, C appears, right? And what happens is that now B, C, and D are all activated, and the edges between them are activated, and the edges basically create a 2 simplex. So this triangle is filled. There is no loop here because this becomes a simplex in your graph, a higher dimensional, let's say, node. But there is a 1-dimensional hole between AE and that simplex. So we still have the 1-dimensional hole here. If you increase it to 100, what happens is F is activated finally, and the edge between F and E is activated. But beyond this, nothing happens. So what is the difference between, for example, node and edge activations? In node activation, we were going to the maximum scale and beyond, and then all the nodes were becoming a simplex. In a sense, everything was becoming a point. In this node activation, however, you see, you can increase the threshold, and A and C, for example, will not be connected. So the hole will persist forever. The hole is not closing. So 2 different ways, edge activations and node activations. In edge activation, if you increase the scale, eventually everything becomes connected and you have a dot. In the node activation, you increase the scale and nothing happens. So the simplices that should appear, but otherwise, A and C, for example, will never get connected. So here also we have multiple questions. How do we define node activation values? This is actually not a challenge. That's actually a good thing, because in many articles, if you have domain values for nodes, they have been found to be quite useful. For example, in molecular networks, people use atomic weights of molecules. For example, carbon has an atomic weight of 12, oxygen has an atomic weight of 16. So if I increase the alpha threshold from, let's say, 12, or we have 1 here actually for the hydrogen, from 1 to 15, hydrogen will appear in the first scale, and then carbon will appear eventually, and then the oxygen will appear. So you can see the filtration happening along these atomic weights. The molecule here given is caffeine. And in this case, for example, hydrogen will appear. No, there is no hydrogen. N was 32 or 52. I don't remember from high school. It was something like this. Oxygen will appear first, and then N will appear. And here we also have double edges. So these mean there are double edges between them. So being able to include domain information like this is quite an important aspect of sub or super level filtration. In the sub, we were going from minimum scale to the maximum scale, remember? To the maximum. In the super level, we go from maximum to minimum. But they are almost identical, however, they give different simplicial complexes. Now, the second question is, should we use sub-level filtration or super-level filtration? Usually, researchers apply both of them and concatenate vectorizations. Question 3 is, how do we define these node activations on directed or weighted graphs? So we need to define node features based on their edges if the network is directed or weighted without node features. This is a common issue in weighted blockchain networks where we apply persistent homology. So now I will, in 2-3 slides, I will give you a few tips and insights for TDA. The main goal is to avoid confusion that arises from divergent perspectives between researchers in the fields of mathematics, statistics, and computer science. And here is one example. In mathematics, a k-dimensional simplex is defined as the convex hull of k plus 1, a finally independent points in k-dimensional space. In graph theory, a k-clique refers to a subset of k vertices in a graph where every vertex is directly connected to every other vertex in the subset. I have shown you these images before. So a dot is a 0 simplex, an edge is a 1 simplex, a triangle is a 2 simplex, a tetrahedron is a 3 simplex. However, if you go to computer science, in computer science, an edge is called a 2-clique, a triangle is called a 3-clique, a tetrahedron is called a 4-clique. So when you are reading TDA papers, beware of this. The second thing is a k-dimensional hull requires vertices with at least degree k plus 1. So we are using, let's say, Viator strips here. As you can see in this graph, there are 2 holes, and then there is this node F. As you can see, node F is never going to create a one-dimensional hole because it has just one edge. In order to create a hole, it should have had at least 2 or more edges. But it doesn't have. In a sense, if you are working with TDA on graphs, including F in your one-dimensional hole computations is completely useless. That's actually the main idea of our NeurIPS 2022 paper, where we scale pH to large graphs. Yeah. In this case, for example, let's look at let's look at holes when they are born and when they die. Sorry. Yeah. So in this case, for example, this one-dimensional hole, this one is connected, this one is connected, and this one is connected. This dies at 60 because this becomes, in a sense, a simplex. When is it born? Well, it's not really born, so I have made a mistake here. What I mean is that this simplex becomes, this triangle becomes a simplex when the threshold is 60. In this case, this one-dimensional hole is born when you have when you are at alpha 3. And then when it dies when the threshold becomes 4. I need to update this slide. So yeah, it's born and then dies. Now, why persistent homology on graphs is powerful? It's powerful because we can track which dimensional features are born and die at what scales. Consider that in computer science, we have this thing called a motif analysis. In motif analysis, we define a motif of size, let's say 3. That means we are going to look at 3 vertices and their edges. Here, I'm showing you the distinct shapes of 3-node graphs in directed graphs. We have a network, and then it can have, for example, 100 nodes or something, and then we go and count these motifs separately. For example, this triangle motif here, it's appearing once here and one here. So we can say that this triangle motif is appearing 2 times. Similarly, this one or this one is appearing sometimes. Motif analysis has been found to be very useful in biological networks everywhere. Persistent homology is kind of a better version of motif analysis, because in persistent homology, we also have the birth and death types of topological features. In motifs, we don't have these things. Traditional motifs don't consider weighted edges or distances. So pH is similar to what we get in graph motif analysis, but with finer quality. That insight is coming from Julia Gal, my postdoc advisor. Now that we have covered TDA on graphs with edge activations and node activations, we are ready to go to the applications of TDA on graphs. I have 2 articles to present here. The first one is a work on Ethereum token networks, and the second one is on the Bitcoin transaction network. So these are 2 different network types. I would like to talk a lot about blockchain graph data structures, but we have a survey paper that you can read. And usually we teach blockchain networks in computer science conferences in 3-4 hours. So in a sense, we don't have enough time to cover this, but I will give you all the essentials so that you will not miss anything. Now, this paper appeared in 2020 in SDM, one of the last papers of my postdoc period. So first, I need to talk a little bit about blockchains, and I need to introduce Ethereum. A blockchain first was created in 2008 in the form of Bitcoin. Bitcoin allowed financial transactions, but Bitcoin did not allow storing data or software code on a blockchain. Then came Vitalik Buterin in 2015. They proposed a new blockchain that can also store and execute code. I believe that most of you are familiar with Ethereum and these account-based blockchain platforms that are account-based. I'm going to now discuss why they are called account-based, what their graphs look like. So similar to Bitcoin, Ethereum has a currency that's called Ether, but there's a code. That's a smart contract that is written in a coding language, and this contract is compiled to bytecode and executed on the Ethereum virtual machine. The code can be as simple as, let's say, 10 lines of code. So these smart contracts are not complicated things. They are quite easy. Yeah. An analogy is the MySQL snippets that are stored on a database. These are the small code pieces that we run all the time, so we store them and run them instead of writing every time. In a blockchain network, a user creates a transaction to upload a smart contract to an address. So address here is what we call a node. The code at the address is replicated in all blockchain nodes, and in other words, you force other users to store your code in their local computer. The code is executed by passing transaction messages to its functions, and the execution occurs at all nodes. For this reason, Ethereum is also known as the world computer. Creating a contract is expensive, but all the calls to the contract code are built in terms of what operations they require and paid by the transaction creator. And here is, for example, some of these operations in computer science. That means, for example, these are the opcodes, and each opcode has a has a cost. It can, for example, cost 3 gas, 5 gas, and so on. I will not go into this, but what it means is that if your transaction is complicated, you pay more money. So why do we have smart contracts? Smart contracts are useful because you can put your code publicly so that it can be analyzed by everyone. Your code cannot be modified without leaving a trace on the blockchain. And the code will run to completion because the run is happening in all the computers connected to the network, not only in your computer or someone else's. And furthermore, the results can be verified by all parties because they run the code themselves and see the results. For this reason, you can see why smart contracts were called smart contracts, because platform creators thought that they would be used to define business agreements. However, the evolution took them somewhere else. So smart contracts, when they became available, people started to create smart contract-based tokens. These tokens are exchange data units that are used to buy or sell services in the real world. For example, the storage token stores files on your hard disk and pays you a fee through Ethereum. So in a sense, you open your dead storage, empty storage to other people. Tokens can be bought or sold, and they act as value stores. Token prices are arbitrated in the real world. That is similar to everyone or you creating a smart contract to create your own asset and then sell it to people. And then there is real arbitrage in the real world where people sell and buy these tokens so that your token will have a price in the real world. Companies even created tokens and sold them in initial coin offerings to raise capital. This is all covered in decentralized finance. So I will tell you how these tokens look like, what their transactions are, and how we can do persistent homology on them. Account-based blockchains basically have 3 types of transactions. In Bitcoin, there is just one type of transaction, a money that changes hands. Then there is the Lightning Network on the Bitcoin, but let me not go there. So in practice, there is just one type of transaction. In Ethereum and other account-based blockchains, we have different types of transactions. The first transaction type is the transfer of the used currency, which is Ether on Ethereum. Like Bitcoin on Bitcoin, we have Ether on Ethereum. So this is the native digital currency of the blockchain. That's the first type of transaction. And the second type of transaction, we have internal transactions, which involve a transfer of smart contract-based tokens from addresses to addresses. A third type is traces that I will not cover, and it's not much studied yet. But let's look at the first type of transaction. These Ethereum graphs are very similar to social network graphs, in the sense that there is just one address sending money to another address, so you can use just 2 nodes and an edge between them to denote the transaction. An address spends coins from a balance and keeps the change. Each transaction of an address has an order. So for example, if this address has multiple transactions, this will have index 0, this one will have index 1, and so on. So you can kind of see every transaction, and when they happen, you can give nice time stamps to them. Okay. Now, internal transactions are a bit different. In internal transactions, there is an ordinary address that is the owner of a token, and there is a smart contract address that is kind of like a bank address, and the bank contains all the money, which are the tokens. Okay. And a transaction can transfer both currencies and tokens, but in internal transactions, let's say an address A is sending 4 ethers to the smart contract address to buy some tokens. And how do we know how many tokens can we buy? Well, it should be defined in the smart contract that says, for example, if you send me 4 ethers, I will give you 20 tokens. Good. So the address buys this, and then the same address may send these tokens to an address B. That means address A is selling tokens to B, and here this shape is a token. Okay. For this, the address sends a message to the smart contract and says, I'm selling my token to address B. So give my tokens to address B. And here are the trading tokens, a timeline. So address A already owns some tokens. Address B wants to buy them. Address B, for example, in this case, is buying sending 0.3 ethers to buy 2 storage tokens. Address A is sending money to B, and B is sending a signal to the smart contract that it should send the tokens of B to address A. These are the 3 transactions happening. Okay. Yeah. At T0, T1, and T2. At the end of the day, at the end of these transactions, the B will have 0 tokens, A will have 2 tokens. And this creates very nice graphs. So if you look at the Ethereum graph, if you put all the edges together, we have these edges. Between A, B, and the smart contract, we can see this transaction graph. And realize in this transaction graph, there are 2 types of currencies. First, we have the ethers, which is the native amount. Then we have the token here, which is an imaginary arbitrary unit. So why is A or B buying these tokens? We don't know. So it can be for any reason. They are investing, they are buying from friends. We don't know. There are so many tokens these days that you cannot even understand what is a token, what it is serving. This kind of transfers actually create a graph that like the one I am showing here. Let's look at this graph. As you can see, it is a weighted, directed graph. There is not really a community structure, because in social networks, for example, we would expect edges between these nodes. We would expect the diameter of the graph to be small, for example. But here it's not the case. And there are multiple edges between the same pairs, because the same person can buy the token multiple times from another person. So these graphs are very challenging for ordinary graph machine learning. When you look at core decomposition in this graph, for example, 99% of the vertices belong to core 1. That means most of them have just one edge, or when you delete the edges, they don't form any communities. The token network is very sparse, devoid of community structure, and daily networks may contain many disconnected components as well. So here I am showing you one graph, but there can be another disconnected component like this. So what we do? Back to the persistent homology. We first say, okay, we have a weighted graph, and we have a node set V and an edge set E. We need to define a dissimilarity between 2 nodes connected by an edge. To account for dissimilarity between 2 disconnected nodes, we introduce a weight that says if 2 addresses have never created an edge, the distance between them is infinity. If they have an edge, the edge weight is the sum of the weights of the edges between them. Next, we are going to say we want to define a WUV with this formula. Here, a WUV is the weight of the edge, a minimum is the minimum edge in the network, and maximum is the maximum. After this transformation, basically we are mapping the edge weight between 2 values. If I'm not wrong, it was between A and B. So this is kind of like taking the edge weights and then converting it to a distance. Okay, dissimilarity. So these values of A and B in this form create a scale. A min and A max are the smallest and the largest edge weights respectively in the network. The idea is very similar to what I mentioned before. So if there are more tokens traded between 2 vertices, which means the higher amounts, the distance should be less. Then we introduce a novel notion of Bethe functions that relate these counts to the scale parameter viewed as continuum. Remember, we were using persistence diagram, persistence silhouettes. We are here defining a new vectorization that we call Bethe functions. A Bethe function that is defined for P from 0 to D is defined as this. So sequence of Bethe numbers are finite dimensional realizations of Bethe functions. That means we are going to look at the Bethe counts at every scale and plot it. And let me show you 3 Betti functions. Here I am showing you the Betti1 functions, and each line is the same network in a different day. So for example, here we have 2, 3, 4 days, and here we have the filtration threshold from 0 to something, and then as we increase the filtration threshold, you will see Betti1 increasing and decreasing. We have normalized the values so that the Betti1 will be at maximum 1 here. So we are not only counting the Betti1, which means one-dimensional holes, we are also normalizing them with the maximum. And if you look at here there are 3 token networks, Tronix, Golem, and Omizego. And they have different Betti signatures. And different Betti signatures, even, they have different signatures on different days. Here the red in the middle, as if you can see, is the deepest point, which means something like the median of these functions over the days that we are considering. Yeah. I will go a little bit into detail about this. Don't worry if you are lost. So the Betti functions can be regarded as a functional summary statistic of the network's topological structure. In this figure, for example, I am showing you the Tronix on 4 different days, February 5, 6, 7, and 8. If I do the scale parameter from, let's say, 0 to something, you see how the Betti function changes in days. For example, in day 1 and day 2, they are similar. Day 3 is a little bit similar, but day 4, something is wrong with this day. Look at how the Betti1 function changes. Due to functional dependency among Betti numbers at different scales, it's important to view this Betti function as opposed to a vector in n-dimensional space. This looking at this Betti function as a, let's say, function instead of a vector allows us to utilize methods from functional data analysis. For example, we can use a functional data depth. Data depth is coming from statistics, core statistics, and the most basic data depth is median. If you have a list of values, for example, you can find the median of it, and which the median is the deepest point in this data. Data depth generalizes this to higher dimensions. What happens if you have 2, 3, 4 dimensional data, for example? How can you find the deepest point of the data? We have used data depth in many applications, but here we are looking at the functional data and we are trying to find which day has the deepest function. From these 4 figures, what can you say? This 4th day, for example, is definitely not the deepest day because it does not look anything like the others. If I have to choose, for example, let's say there are 4 days, and this is the 3rd and the 4th, and the deepest day will be something like this. I am going to order them. I will probably put this as the 1st day here. And I will put the 4th day as the 4th here. So these, let's say, this can be 2 and this can be 3. So if I put them all on top of each other, you can say something like the data that should be something between this 2nd day and the 3rd day. Why? Because in the 1st day, we have a narrow distribution. In the 4th day, we have a wide distribution. In the 2nd day, we have the narrowness a bit decreased, then a lot more decreased, and then in the 4th, we have quite a wide distribution. Data depth allows us to capture this. But before I go further, let me show you a network on the left and their Betti1 functions in the same scale. Here, this blue line is Betti0, the black line is Betti1, and the red line is Betti2. As you can see, in the beginning, we are doing Viatory strips, so all the nodes are isolated. And as you increase the scale threshold, some of the edges appear. That means nodes get connected, so the number of connected components decrease. This is what is happening here, decreasing. As more edges form, you see that there will be some loops. For example, here there will be a loop, here there will be a loop, here there will be a loop that is long. So these loops are starting to appear here, and they continue. And then, of course, after some point, everything is getting connected. So this is dying because 25 here and this one becomes connected in Viatory strips. So this is why they increase and then they start to die. And then we have the second dimensional, two-dimensional holes appearing and dying. If you think about it, these holes that appear here, two-dimensional holes, they don't persist. They immediately disappear. In a sense, they are not the important holes that we want to see. More important holes would be something that appears here, for example, and dies here. So a longer lifespan is important in persistent homology. Yeah. Good. So let's define the deepest point. Consider Bethe functions associated with an evolving token transaction network over days, such as the ones shown here. So each line, each function is a different days Bethe function. Each day visually looks different. However, some days looks like anomalous. For example, look at this day here. This is quite a different behavior than the other days. Why do we have this region in this data here? So we use a notion of rolling band depth to quantify this information. We say we are going to create a Bethe signature, which is defined as the deepest or more central Bethe function. In this case, this red line here is the deepest Bethe function, and we will call it a Bethe signature. This was for the power ledger token. Then we have for the Tronix token. And you see how the shapes are different and the signatures are also different. Now, let's look at our application. We talked about creating these Ethereum token networks and then defining rules on them, and then using Bethe functions and using Bethe signatures to find the deepest Bethe function over days. Our application is actually finding an anomaly in the time series. Given the transaction network of an Ethereum token and time series of the token price in fiat currency, can we predict whether the token price will change more than a threshold in the next H days? And we will identify the maximum horizon value H such that the prediction accuracy is at least rho. So in a sense, we are looking at the network structure, we are looking at the persistent homology, and we are saying today was unlike any other day before. So tomorrow there may be a price anomaly. Either the price is going to increase too much or it is going to decrease too much. If you look at the price returns here on the left figure, we are seeing that most of the time the token price does not change. The distribution is centered around 0. But some days, let's look at here, for example, the price is changing 40%, increasing 40%. Here, this is decreasing 40%. So if we can predict this day, for example, we can make a lot of money. This is the main idea. And if you look at the price anomalies, for example, here we are identifying any change with more than 10 or 15% as anomalous. You see how many different tokens have price anomalies. For example, that day here with the longest bar has seen more than, let's see, how many, 25 tokens with price increases more than 10%. So if you can go to the day before here and then say, okay, tomorrow is going to be a huge price increase, a price anomaly, you can buy these assets and then make profit from it. So our problem is temporal graph anomaly prediction in this case. And here are some of the tokens that we consider: Bytom, Tron, Storage, there are many of them. So we predict anomalies in 31 token networks. A total of 9,042 days are predicted as anomalous. To predict whether the Ethereum token price will change more than a threshold, we combine graph topological features with traditional network summaries. First, we define a price return on day t as the price at day t minus the price at t minus 1 divided by the price at t minus 1. That's quite intuitive. That's actually saying compared to the previous day, how much the price has increased. Then we label a day t as anomalous if there is a significant change. Specifically, if we have more than a user-defined threshold, then we consider the day as anomalous. The good thing is that we build one predictive model for each token. We don't build a general model, we build a predictive model for each token and examine performance for different prediction horizons, h bigger than 0. And for the classifier, we use a random forest and use 2/3 of a token's lifetime for training and backtesting. We create 4 models. In these models, for example, in the baseline model, we only use the price and the edge count in the graph as features. In the second model, we use Betty0 rolling depth. Here, the RD means rolling depth. So we are looking at today's, for example, signature, and we are giving it a value that says today's Betty1 signature is nothing like the signatures that we saw in the previous days. So this is a feature. In the third model, we include Betty1, and in the fourth model, we include Betty2 as well. So if you look at the models, we have Betty0, Betty0 and 1, Betty0, 1 and 2. Okay. And the price, yeah. So if we look at this, here I am showing you a Venn diagram for the number of predicted anomalies in all token networks for the very next day, which means the horizon is 1. So we are looking at today's data to predict tomorrow's price anomaly. And the intersecting regions here indicate agreement on predictions. In this case, for example, it says 51% of the 51% of the models agree on one price anomaly. Okay, look at here. M1 actually creates 35 predictions that are not shared by the Betty models. And what else? M2 creates 7 price anomalies that are not shared by other days. So for up to 3-day horizons, all the models have more than 70% accuracy. Here in this figure on the left, I am showing you accuracy on the y-axis and the prediction horizon in the x-axis. That means if we are trying to predict the price anomaly of tomorrow, we have a huge accuracy. As the prediction horizon increases, the accuracy becomes low and low. Why? Because there is not any signal in the graph of today to predict, for example, 7 days price anomaly. Activity is important, but activity has also a horizon, let's say. You cannot predict something with today's data. You cannot predict too far ahead. Okay. The figure shows that compared to other models, the full model, which is M4, has the least deteriorating performance. So M4 keeps having the highest accuracy, but still there's not enough. The accuracy, however, for Horizon 1 is important, and it offers evidence that Betty models are more conservative in making anomalous day predictions. And their accuracy is better than the baseline model. So here, for example, the baseline model is making these 35 anomalies that do not really happen, but Betty models do not have these false positives. So this was the work on Ethereum token networks. And I will present this one more paper before we leave. But as you noticed, on Ethereum token networks, the graph looks like a directed weighted multigraph. That means it is quite easy to actually apply persistent homology. You just need to define a distance. And imagine in decentralized finance, where you have node features. For example, nodes are addresses, and the address features can be, for example, how many days this address has been active in the blockchain community, in the transaction network, and so on. You can bring such rich information to persistent homology. I believe that we have not even seen the full predictive power of persistent homology yet. In these token networks, there are so many edge and node features that we can use. Decentralized finance is a huge area with billions of dollars. And still, we don't have really analytics companies that can guide users with price predictions, anomaly predictions, and so on. There's a lot of promise here. And these token networks, we share them on our Chartalist website. So if you go to chartalist.org, a link is at the end of my presentation. But let me also write it here, chartalist.org. These token networks are already there, so you can test your algorithms. Chartalist.org. Okay, so let's go to another blockchain, Bitcoin. This paper appeared in 2019 in the ICDM. I presented it in Beijing. That was before COVID. So one starting point for this work was this. Can the blockchain activity of addresses in transactions and blocks be useful to detect and predict phenomena on blockchains? So the first question is, how do we model on-chain data? Because Bitcoin is not like Ethereum. On Ethereum, we had these nice graphs where transactions were between one node and another node. Here I'm showing you a Bitcoin transaction. Let's focus on this top left first. Here you see a transaction where a user, this is a user, is sending 0.8 Bitcoins to user A and 2 Bitcoins to user B. So Bitcoin is a bit strange. In Bitcoin, you have transactions where someone can send Bitcoins to multiple people in the same transaction. So the transactions can be end-to-end. Here I am showing you, for example, a 1-to-2 transaction, but 2 people can send money to 2 people, 2 people can send money to 1 people, and so on. So transactions are quite rich. And in graph terms, we represent the transaction with this structure here. Here you see the address nodes, that is A and B, and the sender address. And then we have a transaction node in the middle. This is the transaction node. Why do we need this in the middle? We need this in the middle because by definition, the creator of Bitcoin, Satoshi Nakamoto, designed the transactions in a way that is not obvious which address is sending money to which address. Let's say I have a transaction with 2 addresses like this. You cannot know, by just looking at the transaction, you cannot know if this guy is sending money to this guy, or this address is sending money to this address, or both of them are contributing equally. In a sense, this transaction node looks like a lake. There are rivers that bring water into this lake, and there are rivers that take water out of this lake. But one-to-one mapping between input and output addresses is hidden. For this reason, I always use this heterogeneous graph. By heterogeneous, I mean there are 2 types of nodes, address nodes and transaction nodes in the graph. In the Ethereum, we have just address nodes. Here we have the transaction node as well, which complicates everything actually. Now, on Bitcoin, once A and B receive money in that transaction, if address B, for example, wants to spend its received 2 Bitcoins, it needs to show proof of funds in the next transaction. It says, here I am, I received 2 Bitcoins from the previous transaction, and I want to use them to pay 1.5 Bitcoins to C and 0.3 Bitcoins to D. Real life is not like this. So if I give you $10, you don't tell me where did you get this money from. On Bitcoin, you need to show this proof of fund. You need to say, I received this money from this transaction here. For this reason, we can actually put all the transactions one after another and create the full transaction network. For this reason, people say that Bitcoin is traceable. So in existing approaches before us, people were using either the address graph or the transaction graph. And in address graph, for example, people were omitting the transaction node in the middle. Let me change the color to red. For example, in the address graph, you will delete the transaction node and just create an edge between the addresses. And this would be like this. Or you could create a transaction graph, and the transaction graph would be something like this. You omit all the addresses. This is the transaction graph. But both of them are kind of wrong, because in the address graph, you omit the transaction nodes. In the transaction graph, you omit the address nodes. So we can do something better. If you think about it, rather than individual edges or nodes, a Bitcoin transaction is created at once with all of its input addresses and all of its output addresses. So in traditional networks, we have nodes that create edges between them, and this is an individual decision. In Bitcoin, this whole transaction structure is an individual decision. Then this transaction structure is another individual decision. Then this one is another individual decision. Then this one is another individual decision. So we have actually 4 decisions here in 4 transactions. So we use something called chainlet to refer to these decisions, these substructures. We define a k-chainlet as a substructure of a graph with k nodes of type transaction. So in this case, for example, if a chainlet structure appears more or less frequently than expected by chance, we call it a blockchain k-chainlet. And a signature of a chainlet is the number of occurrences of the chainlet in the graph. Let me show you an example. Here we have 4 transactions. If you look at it, transaction 1 has 3 inputs and 3 outputs. Transaction 2 has 2 inputs and 3 outputs. And transaction 3 has 2 inputs and 2 outputs. But transaction 4 has the same structure as transaction 3. So in a sense, there are just 3 types of distinct first-order chainlets. By first order, I mean that we are looking at just one transaction and its input and output graphs. Okay? We believe that by aggregating these roles, we can analyze network dynamics. And here is what we do. Bitcoin graph is like this. It is directed, weighted with transaction nodes and address nodes. And then there are addresses which have received coins but have not spent. For example, A7 and A8. In the future, they will create an edge or not, we don't know. So by looking at these chainlets, we can actually count how many transactions were created with the given type. Or if you look at amount, how many bitcoins were transferred with a given type of chainlet. On the figure right here, I am showing you a matrix where, for example, the cell here indicates the number of chainlets, the percentage of chainlets where there are 1 input addresses and 2 output addresses. So for example, this is the output addresses and this is the input addresses. So this is 1, 2, 3, and so on, 4, 5, 6. And this is also 1, 2, and up to A6. So for example, if a transaction has just 1 input and 1 output and 2 inputs, this would be a 2-to-1 transaction, and this would appear here. As you can see, 57% of chainlets on Bitcoin from the history are 1-to-2 chainlets. So someone is creating a transaction from its address, paying another address, and then spending rest of the money somewhere else. Okay, this important information is quite useful. So let's take 1-to-2 chainlets, for example, this one, C1 to 2. How many times this chainlet appears in this graph that we have here? If you look at it, transaction 3 and transaction 1 have this shape, 1-to-2, right? So the occurrence information is 1 here, which is 2 chainlet occurrences. If you look at amounts, how many bitcoins are entering the system, exiting the system, we will see that, for example, 14.4 bitcoins are transferred by them. We can do this for every chainlet type, and then we can record one occurrence matrix where we count the number of chainlets, and one amount matrix where we count the total amount being transferred by using these chainlets in the 24-hour window. And it looks like this. So in the occurrence matrix, we have this information. In the amount matrix, we have this information. Yeah. I will take, I think, around 10 more minutes, so we are in time. So topological data analysis, we already talked about this. Persistent homology gives a nice framework to study these structures. The primary idea is to assess which features remain persistent over a larger set of scales and that are likely to play a significant role. So we propose a novel approach that computes the Bethe sequence on a network of n times n nodes, where n is the size of chainlet matrix A. For each of the unique chainlets, we create a node in a new network, where edge distances between 2 nodes is computed with a suitable distance. So we are taking the Bitcoin network, we are creating a new chain net matrix out of them, where each one is a node itself. When constructing the new network, we use and retain the amount information from the blockchain network. In this way, we actually combine distance with edge connectedness while restricting the network size. So in a sense, we are taking the full Bitcoin network of a day. We are creating a new chain net graph out of them. And on this chain net graph, we can do persistent homology. So this is actually quite a scalable way to apply persistent homology to a very large graph. Okay. We describe the main steps as follows. Given a blockchain network with transferred Bitcoins, we convert all the amounts from Satoshis to Bitcoins, and Satoshi here is a unit of Bitcoin. For example, it has the same role as a cent in a dollar. And we log transform it because Satoshis are very large. There are 100 cents in a US dollar. There are 100 million Satoshis in a Bitcoin. So 10 to the power of 8 comes from that. For each chain net of a given time period, we compute the sample quantiles for the associated log transformed amounts. And a kth Q quantile is the amount such that this equation holds. Okay. And similarly, this tau here is the total number of transactions. So we are looking at the amounts and so on. This detail is not that important. What is important is that we are defining the similarity between chain net nodes in a quantile-based distance. And then we construct a sequence of scales over the chain net metric, chain net graph. And then for each epsilon threshold, which is the same thing as the alpha that we covered before, we built the corresponding VR complex whose zero simplices are single chainlets and vast simplices are pairs of chainlets with less than epsilon k. As a result, we actually have a nice Viator-Rips filtration over the chainlet graph, where we can compute Betty numbers, Betty 0 or Betty 1 over these epsilons from epsilon 1 to epsilon s. Yeah. So in the experiments, what we do is we take a set of features computed on the Bitcoin blockchain, and we are trying to estimate Bitcoin price for a horizon, similar to what we did in Ethereum. However, in Ethereum, we were predicting anomalies. Here, we are predicting the Bitcoin price directly. Our data comes from our own installation. We download and parse the entire Bitcoin transaction graph, and we use a 24-hour window and create daily transactions on the network and create daily Bitcoin graphs. We use the USD price for the Bitcoin in our price prediction. In addition to the features that we have, we actually use past price and transaction count and some other features like mean degree of addresses, number of new addresses in the blockchain, and so on to predict the price. We use a few time series models, for example, Arimax. We use random forest, which is not a time series model, but performed surprisingly better than everything else, XGBT as well. We use a time window-based approach in price prediction. Here, what we say is that we use, for example, a trailing window of 3. We use these 3 days data to predict the very next day. So the horizon is 1. Or if we predict the price in 2 days, our horizon will become 2. Quite a typical time series prediction task by using persistent homology features. Now, these results are interesting because so far I have, like, this work was in 2019, but I have not seen anyone reporting smaller RMSE values. Here I'm showing you the root mean square error for different models for different horizons. Window 3 means we are using the past 3 days data to predict future. Window 5 means we are using the past 5 days data. If you look at it, ARIMA is not working well. Random forest gives the best results, RMSE. Gaussian processes also, Gaussian processes gives the best results. Here, the random forest gives the best results for here. Gaussian processes also look nice. Okay. So we report the percentage predicted gain or decrease in RMSE for a specific machine learning model. And that means how much our features, our new model, is improving over a baseline model. And as you can see here, interestingly, our gain is not always positive. That means over the baseline features, which is the past price and the number of transactions in the system, actually predicting the very next day is not always a good option. Look at this one. It's always almost in the negative. So we explain this by this fact. If you are sick, if you have gotten a virus, you don't immediately become sick. So it's useless to test you immediately because the virus will hatch and then it's going to reproduce and so on and make you sick maybe in 2-3 days. On Bitcoin, we see the same thing. The network activity translates into price activity in 2-3 day horizons, the soonest. So here we report positive values, for example, for Betty model, which is the blue one here. And yeah, and over the week or something, the gain is much higher. These figures are for different windows, but we found that window of 3 or 5 is better because computationally it's also cheaper. But the main point in these figures is that you need to predict the horizon for bigger than 1. So do not try to predict the price tomorrow because the network activity does not have enough clues for that price change next day. So we achieved the best results with a training length of 100 days into the past. That means if you use the full Bitcoin data to predict a temporal price, it will not be useful. Limit your window. Next day predictions do not improve significantly. Our heuristic approach has an interesting trend. So for longer horizons, it gives better results. However, the Betty models achieve better gain values. Our results show that in less than 7 day ahead predictions, topological models have a prediction gain of almost 40% over baseline approaches. And I will stop here and take the questions. This was it for today's class. Thank you very much.
Okay, thank you very much. I'm going to stop there.